All right, so for this week, the support class, we're going to be doing something a little bit different. Normally in this class, we work strictly on prerequisite topics for trigonometry, and we don't really do much in the way of actual trigonometry. It's more about working about the algebra and the geometry, as you already know. But typically, when I teach this class, right about this stage when we're doing trig identities, we've already worked through pretty much all the prerequisites that we really need for this chapter, with the exception of one, solving algebraic equations, which we'll do next week. But because proving trig identities it takes a little while to learn that well. I like to spend a little extra time in our support class just getting more practice on that one topic. So for today, I'm going to go through 3 trig identities, prove those, and then the assignment this week is just going to be doing more of that, proving trig identities. So here's the first one we want to do. I would like to prove the following trig identity. Tangent of theta minus 1 over tangent of theta plus 1 equals 1 minus cotangent of theta over 1 plus cotangent of theta. Okay, now in the parent class we talked about some general strategies for proving trig identities, and the first thing we generally do is we pick whichever side looks the most complicated. And neither side looks more complicated than the other. They actually they look very, very similar to each other. So I kind of think it doesn't matter which side we start from. I'm just going to start from the left side. So let's go ahead and do that. We're going to start by rewriting the left side. Tangent of theta minus 1 over tangent of theta plus 1. Now, something interesting happens here. Normally, what we would do next is turn everything into sines and cosines. And if you were to do that in this case, you could get to this answer, but it would actually take longer than it needs to, and you might actually go down the wrong path if you do that. So it turns out this is one of those kind of rare cases where it's actually better to leave the tangent as is. Now, I want to notice something here. In this identity, in both cases we have a rational expression, so I don't want to lose the fact that this is a rational expression. Also, in the numerator of both sides I have 2 terms, and in the denominator of both sides I also have 2 terms, 1 2 1 2 1 2 1 2. Not only that, in both numerators I have a minus, and in both denominators I have a plus. So it seems like there's actually a lot of similarities between both sides of this. And that actually suggests that there might not be that much that we need to do to get from here to here. The next thing I notice is that in one case I have tangent, and in the other case I have cotangent. And look at where the cotangent appears. It appears as the second term in each one of the numerator and denominator. Well, I already have a minus 1 and a plus 1 there. I could get cotangents to appear here and here just by multiplying this by cotangent of theta over cotangent of theta. I mean, it makes sense, right? Cotangent times 1 would be cotangent. Cotangent times 1 would be cotangent. So I'm getting what I need here. The question is what happens here? So multiplying that gives me tangent of theta times cotangent of theta minus cotangent of theta. Tangent of theta times cotangent of theta plus cotangent of theta. Now comparing this to what we're trying to get, I have minus cotangent of theta and plus cotangent of theta where I want them. It would be really nice if these things could just turn into a 1. But guess what? They can. How do I know that? Tangent and cotangent by definition are reciprocals of each other. What happens when you multiply something to its reciprocal? By definition, you get 1. 1 minus cotangent of theta over 1 plus cotangent of theta, and that's it. The whole thing's done. That was a really quick one if you know the right way to proceed with that. Okay, so that was pretty good. I like that one. Let's try another one. I'd like to prove this guy. tangent of x over secant of x plus cotangent of x over cosecant of x equals sine of x plus cosine of x. Okay, thinking of our general strategies, we want to start with the more complicated side, and in this case there is a clear more complicated side. It's the left-hand side. So we rewrite that left-hand side. Tangent of x over secant of x plus cotangent of x over cosecant of x. Okay? Next thing I'd like to do is use that other very common strategy, turn everything into sines and cosines. And so tangent is the same thing as sine of x over cosine of x. Okay? Secant of x is the same thing as 1 over cosine of x. Plus cotangent, that's the same thing. Remember, it's the reciprocal of tangent, so it would be cosine of x over sine of x. And then finally, cosecant of x is the same thing as 1 over sine of x. Okay? From here, you have complex rational expressions which you can simplify. And if I have a cosine of x in the denominator of each one of these numerator and denominators here, I can cancel those directly. Same thing with the sine of x's here. That leaves me with sine of x over 1 plus cosine of x over 1. But anything over 1 is just equal to itself, and so this is the same thing as sine of x plus cosine of x. Again, it wasn't a super long identity to prove, just took a few steps. And the basic strategies that we talked about, those really common strategies, took us straight to an answer. So there wasn't anything super outside the box that we had to do with this one. Okay, let's try to do one more. Oh, I thought that was a blank page. Let me get rid of that. I need more paper. Here we go. All right, one more. Let's see. I would like to do, I'm kind of picking these from a handout. Okay, I'm going to do this one. Prove cosecant of x plus cotangent of x equals sine of x over 1 minus cosine of x. Okay, so again, the idea here is to pick whichever side looks the most complicated, and in my opinion, rational expressions are usually more complicated than things that don't involve rational expressions. So I'm going to consider the right-hand side to be the most complicated side. So we're going to start with sine of x and put that over 1 minus cosine of x. That's our right-hand side. And then we want to start thinking of what we can do with this. So there's a couple of things that come to mind, but here's one idea. When you have a rational expression, think of that whole thing as just one term. It's just one big term. Everything is clumped together. And we're trying to take this single term here and split it up into a sum of two terms somehow. Well, in order to do that, my numerator has to look like a sum of two terms. That's the very first thing. And I'm not seeing that yet. Secondly, think about cosecant of x and cotangent of x. Cosecant of x is the same thing as 1 over sine. Cotangent is the same thing as cosine over sine. Both of those have a sine in their denominator. It would be kind of nice if I was able to get a sine in the denominator of this. But I don't have that. I have 1 minus cosine of x. So what we're going to do is something that is commonly a helpful step. And it's called multiplying by a conjugate. 1 plus cosine of x. So I already have a 1 minus cosine of x. 1 plus cosine of x is what we call a conjugate for this expression. I'm replacing the minus with a plus, just the opposite sign. And the idea behind multiplying by conjugates is that it's using the factoring technique for difference of squares. Think of this as a minus b and a plus b. We know that that would multiply out to a squared minus b squared, or 1 minus cosine squared of x. Okay? Looking at this should make you think of the Pythagorean identity. What is 1 minus cosine squared of x equal to? we know that it's equal to sine squared. Okay. Now in the numerator here, I'm not going to distribute this sine of x to each of these terms. I'm actually going to leave it in this form, 1 plus cosine of x, like that. Okay. Now here's where I want to use my Pythagorean identity. My numerator is going to stay the same for now, sine of x over 1 plus cosine of x. My denominator, however, becomes sine squared of x. And again, that's from our Pythagorean identity. 1 minus cosine squared is equal to sine squared. Now, notice I have a sine squared here, but I also have a sine of x in my numerator that could cancel with one of those sines. So that leaves me with 1 plus cosine of x over now just sine of x. Okay? And again, remember what we're trying to get to. A sum of two terms, both of which have a denominator of sine of x. We're really close to that point because my numerator has a sum of two terms and the denominator already has that sign. I can take this rational expression and now split it into two rational expressions that are being added together. And this is where we can get our answer. 1 over sine of x is cosecant of x. Cosine of x over sine of x is cotangent of x. Okay, so that's just a little extra practice, a little extra exposure to proving trig identities. Hopefully it gets you a good start on the identities you're going to be proving the assignment this week.